How is everybody doing? I don't know why, but the thing that shows what song is supposed to be playing seems to be super broken. So, that's a thing. I think everything else works though. We'll look into that later. Because, yeah, it's a service. It's not something that I need. So, I don't know. I don't know why it's not working. Hope everybody's having a good day so far. Let me just, I got a lot of things open right now. Where are we going to start today? I think we're going to... Okay. Yeah, it's broken on this scene too. It's broken everywhere. Cool. Cool, cool. So, there we go. We'll start that. So, we are working on a chess program. Just one sec here while I turn down this a little bit. There we go. Okay, so I haven't done too much since last stream. I started looking at different ways to do benchmarking stuff and looking into how bytecode is generated and how that bytecode gets interpreted. Hey, Tursquill. So the way Java kind of works is when you run the compiler, it doesn't generate, like in other languages, it generates assembly. So that's native, right? That's native to the architecture that you're on. So like if you compile something in C++ and you compile it for Windows, it only works for Windows. The big reason that Java cross-platform is because of the JVM, and the JVM extracts abstracts the layer of the, geez, words this morning. I'm still making my coffee, don't worry guys. It abstracts the actual architecture and the hardware. So when we're compiling it, the code turns into bytecode. So if we were to, I can actually show an example of that. So in C++, this code here turns into this assembly. In Java, I believe, yeah, here we go. This is our bytecode. So these bytecode instructions are actually turned into assembly instructions in the JVM by the just-in-time compiler, and that's how the optimizations over time works, as the code kind of realizes. So like if this was, you know, instead of num times num, if it was 1 times 2, it wouldn't keep doing the operation over and over again. Eventually it would just start returning 2. See right here, I constant 2 return. So it's smart enough to know that I don't have to keep doing the math for 1 times 2 every time I call this method. The answer is 2 and it's not going to change. So we're going to have to learn a lot of this stuff. because I don't know a ton of it. So today we're probably not going to dive too deep into that, but that's kind of the route that we're going, and I'm trying to find some resources that are going to be good for teaching that. But let's jump back into our code here. Last time we were playing, so we got a bunch of like drafts, stuff that we don't really care about, but that's okay. So we've got this thing called game bound, which I'm not entirely sure. This is the other thing too. We'll see how much of this we actually use. We're going to clean stuff up as we go. So this is where we got to yesterday. So we got a kilobyte multiplier, and where's our buffer? Here we go. 256 kilobytes is how many we're going to read into the buffer at the same time. And let's see. What did we do? We're going to read the buffer till it's empty, and then we're going to loop through the buffer. Now, there's something else that we could take into consideration here. We're going to be moving very slow because, again, we're learning a lot while we're doing this. It's not just do it. It's learn it as we go. In some other streams, maybe the other people know what they're doing more, and they just do it. But we're going to think and we're going to brainstorm, and I'm just going to bring you guys through the process of figuring some of this stuff out. So 256 kilobytes is an ideal number for reading, but it's not an ideal number for processing. And the reason for that is a lot of hardware performs well in 250-bit kilobyte chunks, but the cache in your processor is the number that we kind of really want to target. So the reason that 256 is a good number is because it's also divisible by common numbers of cache. So 64 kilobytes, that means we can do 4 loop iterations in one read if we can cut this down to processing 64 kilobytes at a time, so we can move it all or access it all in the cache. So I don't know that we're going to see a giant performance boost in that area though, because when I was kind of recording a little bit of the performance numbers, it kind of seems like we're bottlenecked at I/O already, which is the reading and writing. So we'll kind of see how that shapes up. But the way we really want to do these, I wonder here, now let me bring up, do I still have, just give me 1 second here. Let me bring up my terminal here so I can launch something. I need to go to, program. Oh. Okay, so, oh yeah, this is, oh crap, I don't want to do this in Ubuntu. Hold on, I need to do this in PowerShell, which is something I never thought I would say, but I did. I'm gonna go Java, and then this is the, tools. I know you guys can't see. C tools. Yeah. Oh, good, it doesn't open today. I'll figure this out another day. But I was going to show the bytecode difference for if we just flip these two if statements and show that it's actually significantly quicker to put this one first because it's just evaluate not true versus go read the buffer. But that's okay. So what we need to be thinking about here is how can we, what's the quickest way? For now, let's not worry about the cache. We'll come back and optimize that later. We got to do these things one step at a time. So this is the game start. So we're going to put in some comments because I'm already noticing that without comments, when I kind of just jump around and come back a day later when I don't finish the thing, I have to spend a lot of time retracing my steps. So detect start of chess game. And I think there's probably a quicker way. Instead of doing all these like this. So let's already kind of refactor the way this works. Instead of trying to tackle this kind of like top down, like, oh, this is the first part, this is the second part. Let's approach this differently. So if game start found, okay. So if we haven't found the start of the game, we're just going to check. We're going to check the buffer. And let's make a constant for that. Okay. Private static final byte. Open tag. Down here. Move that. I gotta keep kind of remembering that I'm actually using VI and not VS Code. So, and we're gonna check our buffer here. Because everything that we're doing here, we want to make sure that it's a quick in-out. We don't want, it's like this, if the game's not found, it's just going to jump right to the bottom. We don't want to check multi-compounded things. We want quick drills. Okay, let's move this stuff here. So let's do, oh crap. Take that, put that here. Get rid of that. Get rid of this. Okay. So if we're in a game, this is where we're going to need something else to kick us really quickly. Let's look at a PNG really quick. So I've got PGNs, sorry, not PNG. So let's look at a game here. No, we don't need this CSV anymore. So I kind of want to detect this and then I think work backwards, but it's also difficult because we're in a buffer. So when we find this, we want to skip all the way to here and figure out what position this new line's at. So I think what we can do here is, instead of looking for other things, we can well, we can't just look for 0, we can't just look for 1. We need to go backwards. Oh boy. What's going to be the quickest way to do this? We don't want to look for characters that are everywhere. And this result tag could get us. I don't even well, let's talk about that. Let's talk about that. What do you not understand? We can go through it. Like, this is part of why I want to do this. I want to learn kind of together. So like I've got a base level knowledge, but like, well, let's talk it out. Let's go through it. So basic, a lot of it too is you don't have the background knowledge for what we're trying to achieve, right? And why we're doing this. So we can talk about it though. That is the whole point of this. Is I'm learning. I want to teach you guys while I learn, and this is a really difficult project. So like, it is. It's a difficult project that we're going to have to take kind of piecemeal, one piece at a time. So like, what are we trying to do? So like, let's take a look at this here. I want to build something that parses chess games really quick. What's buffered input doing? We'll talk about that. I need to parse chess games as fast as possible. I'm going to be parsing millions of chess games at the same time. And I'm going to be later inserting them into a database, and doing a bunch of other stuff to them, which is why the reading has to be so fast. So right now we're here. We're trying to do a pre-read. We want to isolate where the first character of a chess game is and where the last character of a chess game is. The reason for that is if I know where the start and end is in a big file, so like if we go into this PGN file here, PGN is called Portable Game Notation, so this is a chess game. I want to isolate this first character up here, this open square bracket, and I want to isolate this new line down here. That way I can come back through later and know that between this character and this character is one chess game. And then I want to do the same thing here, and here, and here. The reason we're doing that is we're going to multi-thread the actual processing, and it doesn't really take a long time to read top to bottom. So what I'm trying to do right now is figure out how I'm going to isolate that in as few moves as possible. This class is dirty right now. It's got a lot of stuff it's not using. That's okay. We're doodling around. So this was the first one that I made. And we can go through this really quickly. So this one I made with strings. It's a little bit more straightforward. We're reading line by line. We're looking for, at the beginning, we're trying to parse out just the events. Or not, sorry, events, but tag pairs. So first we're just trying to do those. And then through here we split that line into what it is. So we get the label and the value. And then after that, we try to find move 1 of the game. And then once we're in the moves, we're also parsing out that by ply. So by ply, I mean, this is 1 ply, this is 2 ply, this is 3 ply, this is 4 ply, and so on to the end of the game. You would think that this is probably okay, right? How many lines is it total? Like the whole class is only 57 lines. This can read 250,000 chess games in about 1.9 seconds. Now it doesn't do anything. If we look at this code, like I've even commented out the sysouts, this is just getting down to the flat reading. Just reading, doing nothing else. But we can do better. This example is the one that we're trying to iterate on and do better. So in this version here, we open up like 500 megabytes of memory immediately. We just slurp in the whole file, and then we do it all with bytes. This can process that same 250,000 chess games in 0.9 seconds. So we are trying to make a better version of this. This is definitely the bottleneck right here. creating the strings is the bottleneck in this one. Which, I mean, there's no real getting around because we need them as strings later. So it's something that, but we want to do it as little as possible, is I guess. What we really want to hammer home here is that we want to do it as little as possible. So we're trying to make a better version of this one. And the first step to making a better version of this one is allowing us to multi-thread this. The only way we can multi-thread this is if we know where the games are. Because while this is all nice to, just open up 500 megabytes of memory for the whole file, and this isn't exactly 500 megabytes, it's just silly math, but some of these files are going to get into the gigabytes. I don't want to open up a RAM buffer of 4 gigabytes to process a giant text file. So I need a way, which is what we're doing over here. I only want to open up 256 kilobytes per read. And we may fine tune this, okay? Like, it may not be 256 kilobytes. We're probably going to fine tune it, right? But that's where we're starting with, because 256 is it's a good number that hard drives like to read. It's a good block size. But the cache size of the CPU is 64. So 64 kilobytes is where we're going to target for that. We want a much smaller array size to actually process over, but that's problems we're going to solve in a little bit. Like, I'm pretty sure I'm already bottlenecked at I/O, so I don't know that I can actually measure the performance of actually getting it into the CPU cache, because these tight loops run really fast. So instead now, if we just kind of look at some of this here, we got a couple constants at the top. We've got this thing called portable game notation, which I've started to put some Java docs into. But the idea here is that you've got these things called standard tags. So let's jump out and, well, what is a standard tag? Well, in portable game notation, this is the specification for portable game notation. There are tag pairs, and so like there are 7 major tag pairs, and there are other official tag pairs that aren't part of the 7, but they're still official. So anything that's official, we're going to put in here. We're going to enum it so that we can, realistically, I want the code to understand, but I don't really care if it doesn't have to be a string. If it's a string, it's going to, and that's something that we're going to change eventually, because right now they actually do turn back into strings. Strings are slow. We're going to let this enum its way up, so basically it's just going to be an int in the background. That'll be even quicker. But we're trying to make these portable games. This is ultimately what we want to insert into Postgres later. So did you study, or how did you learn that thing? I mean, calculating how much a method costs. I don't know if I understand the question. Could you rephrase it? What do you mean by calculating how much a method? Okay, so I think I understand your question. This has nothing to do with how much a method costs. I know that the file that I'm processing is 100. The one I'm using right now is 178 megabytes. That's how big the ni file is. If we go to here, this file called ni, this is 178 megabytes, and it could get up to multiple gigabytes in size, just this PGN file. I know through just kind of researching, and I guess, maybe I've got a bit of a, we'll say, edge here. I used to work in mainframe where I/O was everything. So if we we're going to open up a crap drawing here. Crap.draw.io. So I used to work on the mainframe, and in the mainframe, when you're processing something, the way that the hard drive is set up is it's set up in tracks. So when we think of a track is, now I'm going to be very careful because it's been like 7 years since I've had to use my mainframe knowledge, but I believe a track could basically be called one circle of a disk. So like the entire way around a disk is one track, and it's always 30 for a 3390 disk pack, which is a specific size of disk. That's 37,998 bytes per track. So when you're doing mainframe work, you're always very cognizant of the hardware and how the hardware reading and writing works. So if I have something, a file, so if I have a file and the record length on that file, so in the mainframe we call that the LREC-L, the logical record length, is 37,998. That means, so this is my file, every single record in my file, so every line, a line is a record, every time I do one read, I get one record. That sounds pretty good, right? Well, what if I don't really need that much, right? What if, so like, let's do some quick math here. What if my file is actually, let's see if we can be as efficient as possible here. And we'll say that works. So let's say my file, my LREC-L, I don't need 37,000 bytes for this record. It's really small. It's not really doing a whole bunch. So what if I say that my record length is 6,333? Well, that means every time I call the hard drive or the disk, I can actually bring back 6 records. So one read equals 6 iterations through my loop. That's less processing. That's a lot faster. So that's all well and good. That sounds pretty cool, right? So that means that what I was going to do here is I was going to do this. So every single time I do a read, I get this. So, okay, that seems pretty cool, right? I can read one record or I can read 4 records if they're smaller. But what happens? This is where, what happens if I have an LREC-L of 37,999? Any guesses? What happens here? So this is one singular byte longer than the optimal. Any idea what happens? Actually, to make this fair here, we'll do this. Because this is the exact same. And then we'll make this a little more visible here. I'll give you a second to respond and then we'll continue here. But we'll put a big stake through this here. So this isn't actually what happens. This isn't actually what it looks like. Because when I draw this picture, it's like, okay, well, that's just barely the right size. So let's get another one over here just to really drive it home. We'll do that, and then we'll pop this one up a little bit. Okay, so this is the perfect size. These 4 fit in. They're the perfect size. This one's a little bit too big. What actually happens here is this. So this one becomes 37,998. And then this is 1 byte followed by 37,997 bytes of literal garbage. You waste an entire read every single time. Every single time. That's rough, right? So this actually slows down your processing speed by 50%. Right? Because every single time you need to do a read, you need to do 2 reads. That sucks. So if we color these a bit differently here to kind of illustrate it a bit better, look at all this waste. So not only is this wasted storage on your disk, but it's also double the I/O operations to get to it. So when I'm thinking about efficiency and how I want to make something faster, especially when I'm dealing with disk and I/O, the first thing that I want to ask myself are questions like, what is this going to do when I do a read? What is this going to do when I do a write? We don't want this to happen. Now this, and I'll put a big piece of mainframe stuff. So like this doesn't really apply to Java, but this is how I come to how I'm going to process this and how I'm going to think about this. This is my background and why I care about this. So that's all great, but how does that help us here? So because I have that background information, I'm able to start thinking about things like, okay, what's optimal in current architecture? What's optimal on this platform? So this may not be the right number, but this is my best guess at what the right number is right now. We'll fine tune this, we'll do some more research, and at the end of the day, it might be every hard drive is different, but this is a good, solid guess. And then the next thing we're kind of talking about, like, how much RAM is this? Well, this is 256 kilobytes of RAM. That's not a lot. That's good. That's where we want to be, because we're going to need a lot more memory than this, right? If we're parsing millions of chess games, they got to sit in memory, right? So most of my memory is going to be held up with this portable game list, which is where those are going to live. Especially if we're multi-threading this and we've got multiple cores adding to this list, that's going to grow really quickly. So we also need a way to kind of export those out to Postgres as quickly as possible, because we're going to have this tension going on of the reading is happening so much faster than the writes can happen. Right? You get where I'm going with this? The reads are happening so fast that we're filling up memory that we can't actually excise quick enough. So this is where we kind of want that first read that we were talking about a minute ago. So if we go back to the docs here, this pre-read ends up being very important, because now I don't have to process the whole file in one go. I can have a whole bunch of, worker threads that take a game from beginning to end. So now I don't have to fill up my memory from bottom to top. I can say, okay, now that I've cleared this, I know that I have, 7,000 games. Well, I've got 4 threads. So give each thread a game and let it do everything for that game, including the put to Postgres, before it comes back to get the next game. So I know that's a lot of information, but feel free to ask questions. I'm happy to answer them. This isn't necessarily about making quick, fast progress. Or at least I'm learning a lot of this stuff, and I'm hoping that other people can learn a bit about some of this stuff too. So that's why we care about the file sizes, and that's why we care about the memory sizes. Also on the mainframe, you can't dynamically allocate memory the same way. So like if I make a string, I have to know the size of that string before I ever use it. So like I used to have some COBOL stuff in VS Code, but I got rid of it all. Like a pickaxe 9 is 9 bytes long, and it doesn't get any bigger than that, ever. It has to stay 9 bytes for the entire runtime of the program. You have to ask for all your memory up front. So, with all that in mind, we want to be efficient with reading, and we want to be efficient with what's cached in the CPU, because that's how we get these tight loops. Every time I have to go back out to a memory address, it's technically slower. Which I mean is probably fine in a lot of cases, but we're trying to hyper-optimize. That's kind of the goal of this. Even if there's no real perceived benefit, let's try to optimize the crap out of this while we're going. So, when the game is found, great. Now we need to come up with a way to detect the end of the game that's going to be consistent. So, there is no move in chess that starts with a number. So I think what we need to do then is look for the number. I think I need to find a carriage return. Okay, hold on. Let me check the spec. Is the move set always, by definition of the spec, is it always after a blank line? Let's see. Jump over to browse here. Okay. Okay. A move number indication is composed of one or more adjacent digits followed by 0 or more periods. Okay. Does not require move number indications and does not prohibit superfluous move number. Okay, as long as the move numbers are correct. So I don't think each is exactly one game termination marker. So yeah, it's always one of these. Note that the digit 0 is used uppercase. Yeah, the game termination move text. It must match the result tag. Okay, so it doesn't actually say, so I think we have to take that to mean that it doesn't need to be there. Yeah, wait. Okay. Okay. Yeah, we got a maximum line length, but it can be any number of characters lower. I think we just need to look for a carriage return and go backwards. I don't see a way around it. I think that's going to be the quickest way. Like, having read all that, like, when I look at this game, like, I think the quickest way to do this is to say, like, okay, well, let's go here. Is this one of the possible things? No. Is this one of the possible things? No. And then, you know, eventually we'll kind of get down to, like, this could be Queen F1. And if it is, we go, okay, that's a 1. Is that one of the things? Yes. Okay, F isn't. I think that's how we're going to have to do it to make it nice and quick. But we will find out. So let's do... Now, was I... Okay, so just /n. So let's do another one here. Private, static, final byte. New line. We're also going to have to worry about, like... Oh, no. Oh, no. We need to keep the previous buffer. Do some math here. What's the largest? We need to keep the last so many bytes. Shoot. What's the longest one? 1, 2, 3, 4, 5, 6, 7. We'll keep the last 8 bytes. Okay. So let's... we'll call it the loopback buffer for now. There's new byte 8. Okay. And then every time we get to the bottom of the for loop, okay. Every time we get here, we're going to do for int I equals 8, I greater than 0, I minus minus. Okay, and then we're going to say okay. How are we going to get at this? So we're not at the next read yet, but we are out of this. So I is at the end. Actually, this is going to have to be I equals. We're going to have to do this the opposite way, I think. Okay. This is going to be bytes in buffer minus I. Right? Right, that's fine. It's not a statement. Okay. So we want to say loop back buffer 8 minus I equals 7 minus I. Equals that, I think. Okay. So that gives us an extra 8 bytes off the end that we can. That means anytime we get to the end, if the new line is the first character of the buffer that we're in, we can go to the loopback buffer and go back an extra 8 characters to try to discern the end of the game. Okay, so now I think that's what we want. I'm just thinking here. Hold on. Okay. I think that's going to work. So, if the start of the game is found, that's fine. So after we find the start of the game, we're going to say actually, can we I wonder if this is quicker. hold on. Here, sure. Right there. So, what if we do, as soon as we get in here, we do current byte equals, and we don't have to keep going back to the buffer. And then current byte I don't think this has a yeah, okay. And then here we're gonna say current byte equals new line, right? Okay. So if it's a new line, now we have to determine if we're at the end of the game. So now we say if I equals bytes in buffer, and I know this is gross, okay? I know. We're gonna refine this, but first we gotta get something. Now we have to, so if we find a new line, we have to do the loop back buffer. Okay, so how are we going to do this quickly? Like, I know many ways that we can do this, but none of them seem fast. They all seem quite slow. So we can do are we not every new line, I don't know. If we go back one byte, if we go back one byte into the loop back buffer from here, then we can look for 0, 1, 2, or star. Okay. So, let's say loop back buffer 7. Oops. We'll come back here in a second. What's wrong with that? Oh, geez, wrong language. My bad. Okay. So these all require something else, but if we find a star, we did find the end of the game. We can immediately tell that. So so in this case, that means game end index equals total bytes read, because I think we want the new line to be the end of the game. I don't think we need the game end found buffer. I don't think we need this anymore. This is used though. I guess kinda, but and then that's part of the for loop. So we can say, you know what, we will bring this back and we'll say game end found is now true. We'll say if game end found and game start found. For now we'll say continue, but this is going to be, or no, we can do our reset here. So make object, and then we'll say game start found is false. Game end found equals false. Okay. So we're getting close. We're getting very close. But as you can see, like I'm spending more time thinking than coding, and I think there's a lot of current byte. I think there's a lot that we can do with that. It's all about understanding. It's not about going fast. Going fast is good, but going fast means nothing if you don't understand what you're doing. So that one's a dead giveaway, so that's good. So for 2, oh, this now needs a break. So now here we're gonna say loop back buffer 6. If 1 byte back from that equals this. Oops. Okay, so let's use that. Okay, so this is also an end of game found. So for now, I think we're just going to copy. Like, we'll make a method for this later, right? We're just trying to rough this in. We're in visual mode. Okay. Oh crap. I've got to learn these key bindings because, like, I should be able to go faster than this. Okay, this is going to be slash. Okay. Now, it could also be 1-0 or 1-1. Now, I don't believe... Right, so I can just look for 1- and 0-. Now this is also going to get more complicated once we start adding in like annotations and comments and stuff like that. But these two can do the same thing. We can just go back and look for 1. So we can say if that buffer, or the loopback buffer. So I guess we don't even need 8 bytes. We only need 2. For now. Which is interesting. So now we need... Oops. That's still in my paste buffer. Oh, now it's not. Yank it again. Dash. Again, we can rename things later. We don't have to get it perfect the first time. So if equals dash. Okay. So let's think about this. Yeah, we really only need the last 2 bytes. That's crazy. How else can we... Let's just get the 2 that we need. Let's just do that right away. We'll grow it if we need to. And then instead of this, we can do and I equals 0 less than 2. So 0, 1. Oh wait. Yeah, we need... So 1 minus I is going to be first one's going to be 0. We're going to... Okay. And then we can do... Right, okay. That's probably over-engineered, though. That's probably slow. So let's just do this the way that we should. So this is going to be that, and then we'll just do it this way. This actually seems better. There. It was nice when we had a bigger loop, but now it's just that minus 1. And then I'm going to say loop back buffer 1. Okay. So now let's take a look at this. What do we do when we come through? Okay. Just reading here. Hold on, guys. Where is that screen? Oh, there we go. Okay. So let's continue. So now we've got a 2 bytes that we just kind of buffer backwards in case we need it. If the game start is not found, we're just going to compare current byte to open tag. Oh, actually, we don't. That could be current byte. Or wait, we're outside. Where does current byte? Current byte is part of the for loop. Because it has to be I. And this happens outside of that, so we don't have current anymore. That's fine. Okay. Now when we get here, let's, just while we're testing, we're going to say game start index. Game end index. Let's just see if we can get through one game. How big is this one game anyway? This is 797. So we're gonna comment this out. We're just gonna make a much smaller one for testing here. New byte 100. We're just going to take 100 bytes at a time and see if we can do it that way. And then, so yeah, PGN importer. Okay. Comment this out for now. Remember, this is all work in progress. We can change anything. Nothing has to stay. So let's do PGN importer. New PGN importer. Import. Let's make a variable for that. And that's going to be yank, no, yank inside these, and then paste. Cool. Not bad. We are going to learn Vim yet. And then game. Cool. So now let's see if that works. What? Array out of bounds. 96. Okay, let's take a look at that. What? So let's bytes in buffer. Oh, because wait. Oh, it's not 0 index, so this should be -1 and this should be -2. Okay, fair enough. I'm gonna have to turn some of this off. Okay, hold on. We need to take this out. So how am I going to do this? This is where I start to kind of hate the Vim stuff, because I don't. Let's yank this whole line. Or no, let's yank this whole thing. So let's do 6. Do that. Okay. All this JIT watch. I don't usually need the JIT watch stuff, but sometimes I do. So this comes back to here. So now let's come back to here and we'll run. There we go. Okay, so that is running all the way, but it's not doing what I want yet, because it's not. We're never hitting this. We never. Okay. So let's take a quick think here. Okay, so this never happens, huh? Setting current byte. Let's do... time to... Let's figure out what's never getting set. Okay. But I think I can just F5. Okay, so game end is the one that's never ever found. Okay. Okay, so if game start is found, if the current byte... Oh right, this is only if... So there's still the whole other scenario we haven't touched yet, which is if we're okay. If I isn't... Wait. If I equals... We did this wrong. This is for if I equals 0, meaning this is the first. If the current byte is a new line and I equals 0, then we have to go through the loop back. Okay. Let's we need another 2 byte. I think we can... I think what we can do here is say, again, we'll clean this up in a little bit, back to bytes equals new byte. Back 2 bytes, 1 equals buffer Now I think we can say back 2 bytes. I think we can do that. Not quite, huh? Are we finding the new line? In a second here, maybe we'll start... Oh, hold on. You cannot just come in here and do that. You stupid bot. You stupid bot. I don't want a bot. You know what? Get out of here. Get out of here, bot. Bots in chat, guys. Is my whole overlay not working? Nice. There should be chat on screen too. I don't know why it's broken. We'll look at it later. Let's see if we ever get that. Okay, so we never... Wait. We only find... Okay, so we're finding the new lines. Okay. Okay. Little bytes red. So then what is... You know what, let's just... Let's do it this way. Just because I don't believe it right now. I don't believe that it's doing what it says it's doing. So let's just do this here. So if we go back 1 byte and we get a 0 or a 1, back 2 bytes, 0. See what we actually got in there. Oh. So let's see, what do these actually come out to? We're looking for... Right, those might not be bytes. So let's... So let's go, we need what? 0, 1, 2 star. I think are the ones that we need. So we'll do 0, 1, 2, and star. $48, $49, $50, $42. Okay. So now, case 0, 1. I think it was considering these characters instead of bytes, maybe. Let's find a byte chart. UTF-8 to Java bytes chart. Okay, so what do we got? We're looking for 51 and 13. Is there a decimal? UTF-8 byte code in int. Or decimal, not int. Okay, so 51 is the number 3. And 13 is a control character. Doesn't sound right. Another one here. Oh. Oh. Okay, hold on. Int buffer pad equals buffer bytes in buffer minus 1 equals /r 1 else 0 minus buffer pad. What is 13? I need to find a better chart. I know these exist. UTF-8 code table. Why did none of these have... The letter S. Like where, what is this 13? Let's just, I want to try something here. Oops. Whoa. Didn't mean to do that. What I wanted to do though is come back up here and then do this. Turn. Okay, so return is 13. So I was right. What did that do? Why did that jump me back up? What did I push? Okay. Can I do this? Is that a thing? I can. So where am I doing that display? Do I have to do that higher up? I gotta do that here, I think. Oh, yeah, no, I totally have to do it up there. I'm just being stupid. That's all. So we'll get rid of this. And then this has to go up here. Right there. And then... Wait. Has to go here. Because we have to do this differently. Oh no, I was... So we do need to do it down here. We just also need to do it up here. In here. I think. And again, we will make this nicer later, but first we got to get it working. Okay. No? We're still getting 13s. Well, it should be I, not bytes and buffer. Yeah, we still need this here too. Okay. We're getting better now. So, where did I put it? Down. This can come out now. Let's see what we get. We're looking for a 48. 49, 50, or 42. We never find them. Am I crazy? Is this... $93. What's a 93? Is a right squared bracket. Okay. So let's follow this through. 93, 93, 93, 93, 93. Okay. And then a 10. 10 is a line feed, which is this. And then 43, which is hopefully a plus sign. plus sign. And then hopefully 55 is a 7. 55 is the digit 7. 56 is going to be 8. 53 is going to be 5. That all makes sense. 54 is 6. 5 is 3. Or, sorry, here. And then 51 is hopefully 3. 51 is digit 3. Okay, so this is the problem. This is where we find the problem. So digit 3 is 51. Wait. 43. I got lost. Hold on. So 43 is plus sign. 53 is 5. Okay. So we get right to 51, which is, okay, so we get to the penultimate line here. Okay, that's good. Everything else is working. Oh. Duh. Okay. Why aren't we getting... Okay. Something silly's happening here. Is there no new line terminator at the end? Oh my god. At end of file. That's what's happening. Okay, we're just stupid, that's all. Okay. Now we need to if not end of what was this all in this one? Game end found. If not, game end found. Let's just, for now we're just going to do this. We're going to fix it, but for now let's just test this theory. And we are going to do loop back buffer instead. And then we'll refactor this out into methods and make it nice, but let's just get it working. Okay, and then we're also going to take this. Really? Okay, and then loop back buffer, no. 48 is a 0. Oh, shoot. I was right the first time. This actually needs to be fixed up here as well. I was being stupid. There we go. Did it. Got it. Okay. 797. We kind of had a... Is this... 797. Perfect. So from 0... That's not quite right. Because it should be 0796. And we're definitely going to be cleaning this up. But for now, we're just going to go in and hard code all this. Because first again, first step, just get it working. Total bytes read, total bytes read, total bytes read. Game start, that's fine. Total bytes read. Like, we're probably going to break this out into multiple methods, multiple classes, all that fun stuff. Perfect. Okay. Now it parses. Now. To comment out all this stuff, all these sysouts. When did you get here? Editor split thing? Go away. We're going to get rid of all this. Okay. And what we're going to do here is I'm going to put this out here. Now we're going to go back to looping forever here because we want to see how long this takes. Convert to static import, sure. I don't know what you don't like here. Is it just that it's unused? That seems pretty silly, but now we're gonna do we're almost done for today, guys. End time. Why is... Oh. There. That'll fix it. We want to be in here. Go to the bottom. We'll get this. There. I know I'm doing copy paste like a noob, but that is because of I haven't learned how to do it in Vim yet, and I'm trying to go a little bit quick. That. There we go. Wait. There we go. Okay. So let's see how long this takes. So yank, paste. Oh, we also want to up the buffer again here. So let's up our buffer. Okay, so we screwed up somewhere. It doesn't quite work. Oh. So if... Okay. We need another condition. And do else. Else if I equals 1. Then back to bytes. Is oh, this is already getting complicated. So our back 2 bytes becomes 1 byte from the buffer. So buffer 1 equals buffer I minus 1 back 2 bytes 0 equals loop back buffer 1. Oh God. Okay, if I minus 1 minus buffer pad less than 0, then actually, we can just jump straight to 2. So if that's less than 0, then we have to do 1 and 1. Oh. Okay, this is... we can't do it like this. Now we need to come back and rethink how we're doing some of this. We're getting there, but in about 10 minutes, that's where we're going to end for today. So, yeah, this is where we're probably going to just start winding down. So where the issue is right now is that we need to kind of stop doing all this randomly. We got it to work on one game. Actually, let's make sure that we're still in that state. Does it still work with one game? So let's... it does. Holy fast. Right? Look at that. So this is nanoseconds into milliseconds into seconds. But let's just do nanoseconds here. That's pretty fast. That's pretty fast. Let's take a look at it with Visual VM here. Let's comment out the time thing, and we'll open up Visual VM. Let me just get it rolling here. I was gonna push a button. Where's my profiling? Here we go, profiler. So let's start this up. There we go. Okay. So, look at garbage collection kicking in. Okay, we can do better than this. Maybe not today, but I think we can do better than that. Ooh, look at that. We're only using half of the heap. Yeah. Okay, we will figure this out. It's probably not today, because we are ending. But where we've gotten to is one game works, many does not. And the reason that many are not working right now is because of how we're doing a lot of this stuff. So we're gonna have to clean it up and like farm it out into methods so that we can call them a bit better and actually track what's going on. But it's all about how we're calculating this. We might want to go back to a bigger loopback buffer. Okay. I think I know what we need to do, but we're not going to do it today because I am busy today. But this was pretty good. I'm pretty happy with where we got. We definitely got a lot of thinking done here. We also... Actually, let's see how this profiles back down at 100 bytes before we end for the day. So let's reload this. Yeah, see, this is much better. It's because we had it was all about that byte array at the start, so still pretty jagged. Be nice if we could just kind of use like a steady 100 megabytes or something. I don't like necessarily that we continually change our memory usage. That kind of looks not good. But like everything's roughly static. We're not really doing a ton. But we will definitely be able to diagnose that and figure it out. But that's all I've got for today, so you guys have a good rest of your day. I might be back later, we'll see. But I'm definitely done for right now. So we're going to save this, and we will come back to it. For anyone, just kind of while we're finishing up here, for anyone who's just joining, we're building something that'll parse chess games and store them in a database, and eventually we're going to get into some, comparing positions at various moves and stuff like that. But step one is understanding the portable game notation spec and actually parsing it efficiently. So we've got a bit of a drawing going on right here. We're currently doing this box right here, which is pre-read defined the start and end of each game. And then once we have that, we can start multi-threaded game parsing, which I think will be great. But yeah, tomorrow night we've got some Dungeons and Dragons lined up at 7:30 Eastern. We're going to be doing a one-shot, so be sure to check that out. And if you guys liked watching me program and kind of talk through problems, again, ask any questions you want. It's all good. We're figuring things out. We're learning together. But if you guys liked this, maybe give us a follow, or if you're on YouTube, give us a subscribe. You'll see when we're online. We do lots of other stuff. D&D, we do some gaming content. We're starting to do some programming content. We're also in the process of making a game, so eventually I do plan to stream some of that as well. Yeah, lots of fun stuff going on. So if you guys enjoy any of that, definitely subscribe, follow, depending on what platform you're on, and I will catch you guys next time.